Good evening, everyone. Welcome to NPTEL tutorial session on the course Principles of Organic Synthesis taken by Professor T. Punniyamurthy. So, this is our week 12 tutorial session. So, in the week 12, we have seen 5 videos in total, which was about the reagents containing sulfur, silicon, boron, tin, and free radicals. So, in the first lecture, we have seen the reactions of sulfur and silicon containing reagents, where we saw that some sulfur containing reagents and its importance, like penicillin, which is used as an antibiotic, then glutathione, which is used as a scavenger for toxic oxides, then dapsone, which is used as a water soluble prodrug for leprosy. And we have also seen preparation of sulfurilides, reactions of sulfurilides with carbonyl compounds. So today, first we will be having a discussion on some of the named reactions, basically, which have been discussed in the week 12 lectures. Then we will move on to some problem solving related to those topics. So the first reaction which we saw was Julia reaction, and so based on sulfur reagents, we have seen this Julia reaction as well as Korey-Chaykovsky reaction. Then with silicon containing reagents, we have seen Peterson olefination. So in the about the first lecture, we will be discussing on these three reactions first. So first one was Julia olefination. So it is basically, as written here, the addition of a phenyl sulfonyl carbanion to an aldehyde or ketone leads to an intermediate alcohol which is esterified in situ. The reductive elimination with sodium amalgam to furnish the alkene takes place in the second step. So as we can see here, we have a here we have a phenyl sulfone, and this phenyl sulfone, upon treatment with this base, it will abstract this acidic proton, and that will add upon to this aldehyde, and we will be getting an intermediate alcohol which is esterified in situ by this alkyl halide we are using. And then this like reductive elimination we are doing with the sodium amalgam, which will result in the formation of this alkene. So the basic mechanism for this reaction is that, so first, as we discussed, this n-butyl lithium will abstract the proton of this sulfone, phenyl sulfone, to create this phenyl sulfone anion, which react with this aldehyde. So this will attack. So this will attack over here to form this compound, and then again, when we are treating with this R3X, where which is any alkyl halide or any R3 source, so it will, this O minus will be converted into OR3, and in the presence of sodium amalgam and mercury, what will happen? This bond is getting homolyzed, homolytically cleaved, and this is also leaving, like maybe we can say this bond will come here and this bond will come here, and we will be getting this vinyl radical species, and which upon protonation in the presence of this ethanol solvent we are using, we will be getting this alkene. So here we have written the stereochemistry of the alkene is independent of the stereochemistry of sulfone intermediate. It is thought that the radical intermediates are able to equilibrate so that more thermodynamically stable trans-olefin will be the major product in most of the cases. So, since the trans-olefin is forming, we are expecting that this reductive elimination is happening through a radical pathway. So, it will be mostly favoring this formation of E-alky. So, this is the Joule olefination. Phenyl sulfones, upon treatment with this base, will generate the corresponding anion, which will add upon to the aldehydes, followed by esterification, and then um, reductive elimination will be giving this alkene. So that is Julia olefination. I'll give you 2 minutes to just quickly go through this, then we will move on to the next reaction. I hope this is clear. Now moving to the next reaction, that is Corey-Chekhovsky reaction. So here what is basically happening is that the sulfur halides upon treatment with this DMSO, depending on the starting material, either it can give this epoxides, aziridines, or cyclopropanation. So, if we are treating it with a carbonyl compound, we will be getting epoxide. If we are treating it with an imine, we will be getting this aziridine. And if we are treating it with a double bond, then we will be getting this cyclopropanated product. So, this is basically Corey-Chekhovsky reaction. Now, we will see its mechanism. So for this Korey-Chaykovsky epoxidation, so the first step is basically the same. This sodium hydride will abstract the proton of one of this methyl group, which is beside the sulfur, and it will form this double bond, which can exist in this form as well, S plus and this CH2 minus, and then this negative charge will attack on the carbonyl carbon, and that will form this intermediate. And then what is happening, this O minus is attacking at the CH2, and this is leaving as this dimethyl sulfide. So we will be getting this epoxide as the product. So the first step is the formation of sulfonium halide, that is this one, by using a base, and then nucleophilic addition of the halide to the carbonyl carbon, and then this oxirane formation. So that is the mechanism of Corey-Chaykovsky epoxidation. Now, if it is Korey-Chaykovsky cyclopropanation, basically it is the same. That is, the halide will be attacking over this alkene. That bond will shift to here, and this will shift to here to form this. Then, when this O minus will come back, this double bond is going to attack the CH2, and this will be knocked out as this DMSO. So we will be getting the cyclopropane formation. So here nucleophilic addition of the halide to the carbonyl carbon was taking place. Here conjugate addition of the halide to the enone was taking place. And for acidination also the mechanism is similar. So this is Korey-Chaykovsky epoxidation and Korey-Chaykovsky cyclopropanation, which is using this sulfur halides. Okay, so that was the reactions about this sulfur elites basically. Now moving on to another reaction which is having this reactions about the silicon containing reagents. So that is Peterson olefination. So here what is happening is that first this silyl lithium is being formed, that is I will go through the mechanism. We are treating this here will be the halide. So the proton abstraction will be taking place, not proton abstraction, that Cl minus elimination will take place when we treat with some lithium species. We will get the silyl lithium, and then that 1 to addition over this acid, or 1 to addition over this carbonyl compound, we will get this eliminated product, that is known as Peterson olefination. So what is happening here is that this TMSCl, when we are treating with this lithium, first it will form TMS lithium species, and that will undergo this addition of 1 to addition over this aldehyde, and we will get this compound. Then upon treatment with this PPH3 CCl4, that is basically Appel reaction, which convert this hydroxyl group into this chloride. Then upon treatment with this magnesium, this MgCl is formed, and then that will again add upon to the next aldehyde to form this species, and this upon hydrolysis we will get this alcohol. Now once we have this alcohol, either in acidic condition we will get this anti-elimination product to get this alkene, and if this O minus is getting formed, and this O minus will coordinate with this silicon of this TMS group to form this intermediate, and then a concerted syn elimination will take place to form this eliminated product. So it depends on which mechanism it is following, will depends on acid or base. So the key intermediate is this one, this hydroxy compound, that is this alcohol. If we are treating it with base, then this concerted syn elimination is happening to get this alkene, and if we are treating with acid, this type of anti elimination is happening to get this alkene. So this is basically Peterson olefination. This silyl lithium complex, 1 to addition on aldehyde, then elimination, which can occur in two different pathway depending on whether we are using acid or base to get this alkene as a product. Now, in the second lecture, basically we have seen the preparation and reactions of organoboranes and organotin reagents. And in boron-containing reagents, we have seen hydroboration, oxidation, then coupling reaction. And in organotin reagent, we have seen another coupling reaction, that is Chile coupling. So first we will see the hydroboration oxidation of alkenes. So in hydroboration, what is happening is that this, we have an alkene here. So, and we have the borane, which is BH, and this will add across this carbon carbon pi bond. So one will add on this carbon and hydrogen will add on this carbon. So how it is adding, it will be adding in a syn addition, and the hydrogen is derived to more substituted carbon, that is in an anti Markovnikov's regioselectivity, because boron will be always attracted to less sterically hindered carbon or less crowded carbon. So we can say this is an anti Markovnikov's addition, because hydrogen will be going to the more substituted carbon. Then the resulting organoborane upon oxidation, we will be getting this carbon boron bond replaced with the carbon OH bond with retention of configuration. So this is happening. So first alkene, this BH is undergoing addition over this alkene. Since this is having R group, this will be delta plus, so hydrogen will be added to this carbon and this carbon will be bonded to this boron. So we will get this in addition product. Now upon oxidation using this peroxide in NaOH condition, we will be getting this alcohol as the major product. So here carbon oxygen and carbon hydrogen bond is formed by breaking this carbon carbon bond. So the detailed mechanism is like this. First, as we say, the concerted transition state is forming like this. So bonds are breaking and forming at the same time by the syn addition of BH across this alkene. Then hydrogen is more electronegative than boron. Hydrogen, the value is 2.2 and boron electronegativity is 2. So hydrogen will goes to the more substituted carbon, electron rich carbon. uh, so that is, the hydrogen lines up with the carbon, best able to stabilize the positive charge, the most substituted carbon. And then what is happening then, when we are, so after getting this species boron complex, when we are treating with H2O2 NaOH, first NaOH OH minus will take the proton of this H2O2 to form its conjugate base, which is a better nucleophile than H2O2. Then this peroxide will attack on this boron to form this intermediate. Once that is formed, then what is happening, this the pair of electrons in the carbon boron bond attack oxygen. So this bond is shifting to here, and this oxygen bond is a weak bond, peroxide bond is a very weak bond, so it will cleave. That will result in the formation of this species. Then this we can draw as this one. Now this bond is getting hydrolyzed, that is again OH minus is attacking over this boron, and this will come to here to form this O minus. Then this O minus will take up a proton from the water while work up, and we will get this alcohol. So first what is happening, after forming the addition product, this peroxide will generate its conjugate base of H2O2 by, so its conjugate base is formed here. And then this peroxide is attacking over this boron to form this compound. And here then what is happening is that this oxygen oxygen bond of this peroxide is very weak, so it is easily breaking, and this will shift over this to form this species. Then again this OH minus is attacking over this boron, and this will form this O minus, which upon taking a proton from the water molecule, probably during the workup, we will be getting this hydroxyl group. So that is hydroboration oxidation reaction. Moving to the next reaction which we have seen, that was Suzuki coupling. So it is basically the coupling between this organoboranes and alkyl halides in the presence of this palladium, and we will be using a ligand and a base. So here we will be getting this couple product. And here the mechanism is similar to other coupling reactions. First, to this palladium zero, this alkyl halides will undergo oxidative addition to form this palladium 2 species. And then while treating with the base, what is happening? Yeah, anion exchange or metathesis between the anion of the base and one attached to the catalyst is taking place, which will be a resulting in again the palladium 2 species. Then meanwhile this yeah this boronic species will undergo transmetallation with this palladium 2 species to get this compound, that is this OR group is going with this boron to get this complex, and which upon this reductive elimination will regenerate this palladium zero complex, and we will be getting this reductive eliminated product, that is our couple product. Then based on the organotin reagents, we have seen this Stille coupling. So that is the coupling reaction between this tin compound and this aryl halides, which is mediated by again palladium. So here what is happening is the mechanism is similar: oxidative addition of this alkyl halide, which will give this palladium 2 complex, transmetallation with this tin compound to give this, and then reductive elimination will give this couple product. So first oxidative addition, then transmetallation, and then reductive elimination will give the coupled product. So this was the reaction based on organotin reagents. Now, in the third lecture, we have seen about radical reactions and the formation of carbon carbon and carbon halogen bonds. So, there we have seen one named reaction, that is Hans-Dicker reaction. So this is basically the conversion of silver carboxylate into alkyl halide by treating it with this bromine or iodine. And the mechanism is like this. So first, this carboxylic acid upon treatment with the silver oxide will be forming its silver salt, and then this O minus will attack on this Br, and Br minus will leave out to form this compound. Then this bond will undergo homolysis to form this radical species, and then the CO2 elimination, that is this is converting to coming to here, this is coming to here, and that will form this R radical as well as this Br radical, which is eliminated at this stage by the elimination of this carbon dioxide. Then that will combine to form this alkyl halides. So that is known as Hans-Dicker reaction, conversion of silver carboxylate into alkyl halides by the decarboxylation using bromine or iodine, and a silver salt. So this reaction is proceeding through this radical pathway where we can get the alkyl halide from this corresponding silver carboxylate. Then in the last lecture, not last lecture, fourth lecture, we have seen copper, manganese, samarium, selenium based reactions and acyloin condensation. So here we will discuss acyloin condensation. So basically what is happening is that this esters in the presence of this molten sodium metal and TMSCl will be forming this compound bis silyloxyalkyne alkene, which upon this hydrolysis, acidic hydrolysis, we will be getting this acyloid. So that is basically alpha hydroxy ketone. So what is happening here is that this is again a radical pathway. So in the presence of this sodium radical, since we are using this molten sodium metal, we will be getting this radicals, this homo radicals. Then this will undergo this radical will undergo reaction to form this intermediate. Then this O minus is again converted into corresponding radical, and that will result in the formation of this diketone by the elimination. That is, this O minus will come over here and this will leave out, and this O minus will come on here and this will leave out. So we will be getting this diketone, which is again polarized by using the sodium metal. So we will get this ene diol, that is here this will be radical, so that double bond is formed, and this is O minus Na plus. Then upon workup we will get this ene diol, which is basically the tautomerized form, the form of this acyloin. So this is known as acyloin condensation. Now in the last lecture we have seen the carbon nitrogen carbon oxygen bond formation and decarboxylation. So one of the reaction which we saw there was Hofmann Loeffler Freytag reaction. So that is basically the reaction of the cyclization reaction, basically in the presence of acid and heating, and then in the presence of base. So what is happening here is that first this amino compound which will get protonated to form this species, and upon heating this nitrogen bromine bond will undergo homolytic cleavage to form this radical. Then this bond is undergoing homolytic cleavage to form a radical over this center. So these two radicals can combine, or this proton will be taken up by this nitrogen to form this N plus, and here one radical will be left. And then what is happening here is that whatever Br radical which got eliminated, that can combine with this radical and that will form this species. Then when we are treating with this base, that will take this proton and which will stabilize this positive charge on nitrogen to form this species. Then this nitrogen lone pairs can attack over this center and Br minus will leave out to form this compound. Again base will take this proton and eliminate this water molecule to form this cyclized product. So this reaction is known as Hofmann Loeffler Freytag reaction. So in the presence of acid, that amine is getting protonated, then this Br will leave out as Br radical, and again the proton is taken from the alpha beta gamma delta position, and their radical will be generated, which will form again the alkyl, like halide will be formed. Then nitrogen, positive charge on the nitrogen is stabilized with you by using a base which will abstract a proton, and then this nitrogen lone pairs will attack over the carbon where bromine is attached, and the bromine will be knocked out, and then again the base will take up the proton on the nitrogen to stabilize the positive charge to form the product. Moving to the next reaction, which is Barton reaction. So Barton reaction is a photochemical reaction where the alkyl nitrides having minimum 2 hydrogen at the delta position. An example is given here, which upon this photochemical exposure, this bifunctional gamma hydroxy oxime is formed. So we will see how it is happening. First, upon this photochemical exposure, this NO radical will leave out to form this alkoxy radical. Then again, this that can coordinate with this proton, and that will form this OH and a radical at this center through this six-membered cyclic transition state. And this radical will combine with the NO radical which was already left, and then this hydroxy nitroso product can tautomerize to form this gamma hydroxy oxime product. So this reaction is known as Barton reaction. Moving to the next reaction, that is Barton-McCombie reaction. So here what is happening is that this alcohol, upon treatment with this base and this sulfur compound, or with NaH and CS2 and then methyl iodide, we will get this compound or this compound either, which upon treatment with this tributyl tinhydride and AIBN, we will be able to remove all this, thereby getting this alkene. So this is basically dehydroxylation reaction, which is shown here. So what is happening first is that this alcohol will be converted into corresponding sandite ester by abstracting this proton and then treating with the CS2, then treating with this methyl iodide, this will form this sandite, and then in the same time this AIBN upon heating will form this radical, and which will combine with this tributyl tinhydride to form this free tributyl tin radical, and which will add upon this sulfur, and we will be getting this radical. Again this bond is getting homolytically cleaved and this is eliminated, and this will be this radical will be combining with this hydrogen radical from the tributyl tinhydride, and we will be getting this product. So the first step is in the first step, the alcohol is converted into the corresponding thio-oxoester or xanthate ester. Then homolytic cleavage of AABN will generate the radical species that abstract the hydrogen atom from tributyl stannine. Then the tributyl stannile radical abstract the xanthate group, and the resulting alkyl radical abstract another hydrogen from the tributyl stannine, then generating the deoxygenated product and a new radical species. So the reaction will be continued. Okay, so far today we have seen the reaction based on some metals, where we have seen Julia olefination, Korey-Tchaikovsky epoxidation and cyclopropanation, then Peterson olefination and hydroboration oxidation, Suzuki coupling, Stille coupling, Hans Decker reaction, acyloin condensation, Hoffman Loeffler Freytag reaction, Barton reaction, Barton McCombie deoxygenation. So maybe we can conclude the session today with this, and the problems based on this we can uh, discuss in next Saturday, where we will be taking an extra tutorial session for 1 hour. So during that time we can discuss the problems related to this last lecture. So thank you for joining. If you have any questions or queries, feel free to ask. So let's meet on next tutorial session, which will be our last session. Thank you.